Welcome back to another episode of Dr. Erin Explains the Universe. In this one, we're going to be talking about dark matter, the stuff, not the show. So if you're here for the show, sorry. But hang around, because you might learn something. And I'm going to talk about the show at some point in other episodes. So there is love for it, but just not in this episode. So I get this question all the time. What is dark matter? Science fiction throws this term around all the time, and it's easily confused with dark energy. So off the bat, dark matter and dark energy, different things. Totally different things. This one, we're going to be talking about dark matter. So when we talk about matter, we're typically talking about hydrogen, helium, things that are made up of protons, neutrons, electrons, stuff that we can understand. So all of these protons and neutrons that make up elements, this is what we call baryonic matter. It's made of baryons. It's detectable, it interacts in ways that we understand, that we can observe. They give off heat, they crash into each other. We get baryonic matter. It's something we understand. And when we look out the window into the great unknown, stuff that we're seeing is all baryonic matter. So what's the other stuff? Well, it turns out there's a lot of other stuff. That what we're seeing is just a tiny amount. It's actually about 4%. So 4% of everything that's out there is just stuff that we can see. The rest of it is not. A good chunk of it is what we call dark matter. So where did it come about? What is it? We're going to go into the history of it because I can't answer the question, what is it? We're still trying to figure it out. But I can talk a little bit about the history. So as I go into describing some of the history and the science of dark matter, I am going to be referencing a little bit about Spacetime. So if you've not watched my Spacetime video, I recommend that. But if you're comfortable with the idea of like bowling ball on a trampoline, I'm going to be using that analogy a lot. Because I always do, because that's what I do. But if you've not seen it or you're not familiar with that concept, then go watch that video and then come back, because it's going to make a lot more sense. So in the 1880s-ish, Lord Kelvin, shout out for Glasgow, he gave a talk where he had been kind of trying to measure the speed of stars around our galaxy. Now, if you put a bowling ball on a trampoline and you flick a marble around, you can picture if it's closer to the bowling ball, it's going to go faster. If it's further away, it's going to take a longer time to go around the trampoline. Same thing happens with gravity. In our solar system, the planets that are close to the sun move a lot faster around it, and the ones that are further away take a long time to go around. So astronomers figured, and scientists figured, that the further away you got from the center of our galaxy, the slower the stars would go. And Lord Kelvin was kind of making these measurements, and he was giving a talk, and he said, there's a lot of stuff in our galaxy that we can't see because stars are moving really fast. The stars that we can see are moving a lot faster than we expect. So he had no explanation for what that was. He thought it was just maybe dark stars. Again, this is the 1880s, so we're not, astronomers are kind of assuming that they just don't have the technologies to be able to see some of this stuff as opposed to stuff not being there. And so he brought this up, kind of the first mentioned question that maybe there's something dark out there that we can't see. And then this continued, and scientists continued to make observations and continued to study things. And about in the 1930s is when some really detailed measurements started taking place. Telescopes were a lot better. We can look at other galaxies, we can look at clusters, and we can start to measure the velocities. So again, this whole thing is just measuring the speed of stuff orbiting around a center to say, okay, how much stuff is there? We can look at it and we can try to add it all up, and then we can look at the speed and see if that makes sense, if that matches. So Zwicky was one of them that started making these really detailed observations, and he was measuring the speed around the Coma cluster, the speed of stars around this Coma cluster, and he was realizing that it wasn't adding up, that they were going a lot faster. Now his measurements were quite a bit off, and that had to do with Hubble. That the Hubble constant was a bit off. Again, 1930s was a huge expansion of our knowledge in science, so people are learning things simultaneously. But regardless of what numbers he had, the ultimate conclusion was that there has to be more matter there than what we can observe, and our telescopes are getting pretty good. So, okay, what's going on? So he starts postulating that maybe there is something that we can't detect out there that might be different. Whatever it is, there's a lot of it. And so because there's so much of it, there has to be a reason why we're not seeing it by now. So, astronomers kind of sit on it and they try to figure this stuff out. And then we get into the 1970s, and Vera Rubin, awesome astronomer, she was making measurements using a new type of spectrograph where you're able to really make detailed measurements of this stuff. And so she started really detailed counting these velocities and trying to really quantify what that number is. Vera Rubin was one of these who really sat down and made detailed velocity measurements to try to not explain what was there, but try to figure out how much was there. And so she did a lot of great work in this, gave us a lot of great numbers. And so as she solidified all of this and published these papers and saw these numbers, so we're going into the 1980s, which isn't that long ago, and astronomers are saying, all right, people, there's something here. There has to be something that we're not seeing that we don't understand. We're going to call it dark matter. And we need to try to figure out what it is, because there's clearly a lot of it out there. So some theories are floated around. They weren't clever with the dark matter name, but they were really clever with the sort of explanations for what they could be. First one was a macho, massive compact halo object, so machos, that would basically be a lot of baryonic matter. So stuff that we still could detect that just was maybe darker. So maybe it would be something like a brown dwarf. If you remember from my video about solar life cycles, this would be a brown dwarf, or other pockets of dust and gas that maybe we're just not observing. Now the problem is that would have to be a lot, and way more than is actually out there. So that's kind of ruled out. The other option would be what we call WIMPs. So we have WIMPs and machos, weakly interacting massive particles. These are things that are non-baryonic, so like neutrinos. But again, we add up what we know is there, and it's just not enough. So how can we start to understand dark matter when we can't figure out what it is? Well, we can do some pretty cool observations, and the biggest sort of shining example of dark matter is something called the bullet cluster. Now, what this is it's kind of two clusters that have collided. You get this bullet cluster, and we can see this hot radiation from the X-ray of the baryonic matter that's interacted, that's hit into each other, that's heated up because of this collision. And then we can do gravitational lensing, where we see light bend around matter because of gravity. Again, bowling ball on a trampoline, flick a marble, it's going to curve around. Light does the same thing. So we can measure the light that's curving around this empty space and measure how much stuff is there, how much stuff is interacting gravitationally. And we start to realize that not only is there a ton of matter there that we don't see, but it also didn't interact. It just kind of passed right through, whereas you had all these X-rays. So we're starting to put the puzzle pieces together about dark matter. We don't have great explanation for it yet. Still investigating, still doing experiments with the Hadron Colliders, doing particle physics experiments to see if we can see some sort of radiation. But as far as we know, the main way that dark matter interacts is gravitationally. So we have to keep studying that, and we have to try to figure out what it is. So it's a big mystery, it's awesome, and one day it might fuel the Planet Express ship. So that's it for this episode. Thanks for watching, and I will catch you next time.